Drum roll, please. Here's an example. The left motor and the right motor are completely imbalanced, and it died. It went off to the edge and died. So we're going to pick it up and put it back again. But it gets better, folks. It's going to do this a few times. But now it's learned back up, but not quite. Now it's going to try something different. You'll notice it speeds up when this sensor gets to the edge because it's different parameters. And 5 seconds has gone by and it survived. So like that, oh, so now it finally died. So now we set it back again. It liked that because it was moving and survived. So we're going to modify that slightly.
When the sensor goes into the black, doesn't it die?
Black means off the table.
Oh, I got you.
So now it's learned not to die, which is the version 1, but it's not going forward very far. So that's not a, it's a solution, but not a, there's a better solution. Okay, so now we finally learned, oh, when we go off the table, we do basically random things, and we've learned back up a little bit. Not quite enough. It is arbitrary. At 5 seconds, we stop it. If it happens to be off, it's going to die accidentally anyway, even though it had a good algorithm. So now it's going to spin for a bit. It likes to spin because it learned spinning was a good, safe thing to do. Oh, it found the edge, and now it's learned to back up and get back on the table, but not quite in a corner. So you can sort of see it's slowly learning how to stay on the table all by itself. And it doesn't matter about the parameters of the motors. It doesn't matter about the slipperiness of the surface. And now it's going faster. It's learning that faster gets more points. Oh, wow. So now we're going fast and yay.
Phase 1. It's all right.
Phase 1. So here we have a robot that learned phase 1 all by itself in a relatively short amount of time, which is actually pretty impressive. Oh, it doesn't quite know what happens when the left sensor goes off the edge. But it will quickly figure that out too. All right. Cool. Anyway, that's MopBot and learning with genetic algorithms.
Wow.
All of the source code is available. The parts list, this is also all open source. The parts list, 3D files on how to build these. I posted that already a few months ago on the website. So everybody go out and build one and start playing with AI at home. Questions? Yes?
Is that code on GitHub? You said it's on the website.
It's not on GitHub. I posted on the HBRC news group a link. I don't use GitHub, but I store everything on a Google Drive, and I posted the links on that news group. So while I'm fielding other questions, I'll pull it up just so people can see where it is. Other questions?
So you're talking about the black being death, so to speak, but I notice it goes off and senses it, and then it backs up. So it's more like a punishment, not actual death, right? It's like pain.
If the normal table bot only has the 2 sensors, so if it goes off the edge, that's fine. It's just pain, right? And it's going to learn to not be there.
As opposed to a reward.
The third sensor in the middle, the robot really doesn't know that it's there. I've just hardwired
okay.
that if you actually go there, It's the same as, it fell off the table, but I did want to break MOPBOTS continuously while it learned.
No, that, I get you now,
So
that
this was
center
my-
sensor, that's pretty smart.
Exactly, this was my solution to,
Okay.
you died, if it does that in 0.5
Gotcha.
seconds, it's like immediate death. I'm not gonna wait 5 seconds. Whereas if it's on an edge, it's still going for
No, that's
5
valid.
seconds.
Yeah.
So that was just my way of not breaking hardware. Yes?
So I have a Raspberry Pi and I'm looking to make a platform. Is there a platform that's kind of similar with the Raspberry Pi, a controller computer?
I know there are a lot online. I actually bought a Raspberry Pi based robot kit that has ping sensors and these line sensors, so you could do the same thing.
Something not too expensive because I don't want to. That seems like that's a cheap one.
The reason I like this, it's just an Arduino Nano. You can get these for about $5 online. So it's a little bit cheaper than a Pi. Of course, it's a lot less CPU power, but that's why I call this ghetto AI that you can do at home.
Yeah.
Everybody's talking about the great and wonderful things you can do with TensorFlow, and you hear that in this group a lot, and I'm like, I want to be on the other end. Look at these great and wonderful things you can do with an Arduino Nano. You don't really need a lot of CPU power to do artificial intelligence and machine learning, so that's what I'm trying to evangelize.
Okay.
But Pi is also perfectly great because now you've got a camera, you can do other stuff with it.
Well, I already have a Pi sitting around, so.
Exactly, build a robot with your Pi. Same thing I use. Yeah, any other questions?
Appropriate.
Oh, Alan.
How is this different from like some of those really simple beam robots that we saw around 20 years ago that were just like, wasn't even a CPU, it was just switches that sense things. And you could do things like go towards the light or run away from the light based on just a couple of sensors.
Well, that's similar to like Danny's robots. It can go towards the box and go away from the box based on the sensors. And it can even do the tabletop challenge by sensing the edge of the table. It didn't learn. You have to write special code to do whatever behavior you want it to do. So I guess that would be the difference. Is we have state, we have learning, and we can learn new things. I said earlier that you can reuse it without having to write special extra code. You actually sort of do. You have to write your fitness function, you have to write your mutation function. But the meat of what a GA does, once you've written that backbone, it's just replacing those functions, and then you can use this generically to solve a lot of different problems. Even tic-tac-toe and hexapod, not quite checkers.
So I was watching the robot perform, and I'm just trying to think of, it fell off the top table figuratively quite a few times.
Yes.
Why, when the sensor was off the edge of the table, did it not learn right when the sensor was right off the table?
It actually did. It learned when the left sensor was off the table to turn away and get back on the table, and the same with the right. The middle sensor is special in that the robot in the genetic algorithm code wasn't really aware of that.
No, I understood that,
Yeah.
but I was thinking that as soon as it went from on the table to off the table, that it might just back up then.
And it learned to do that. Now the issue is how fast should it back up, and for how many milliseconds should it back up? One solution might be, when I'm in this state, back up in short bursts, and it might actually stay in that state for a few milliseconds and back up, and it will eventually get there. But as an optimization, we want to get off as quickly as possible, and it's going to basically randomize its speed until it finds the best one. But eventually, that's exactly what it did. It learned to back up.
So in this example, when the left sensor went off, it tried left and failed. And then the next time the sensor went off, it knew that was a bad choice and maybe went left, actuated the left wheel forward to keep it try it the other way.
Sort of, but
Okay.
not really. The way this version works is it went off this way, and of course the solution is to back up.
How did it know that without guessing?
That's the point, it guessed.
Okay, it guessed.
And so once
figured
it
that
guessed
out.
properly,
Mm.
and the next time, if it went to the left, it didn't remember that, really. All it knew was that's a bad thing to do, and it erased it. It got killed. That
So
object
it
was
learned the
deleted.
positive motion, not so much that going the opposite way is a negative.
Yeah, but it learns. Let me pull bugs back up because that sort of illustrates a good point. You'll notice that the bugs started whenever there's a high density of grass. The cloud of bugs sort of slowly ate that grass. And it wasn't that it learned to go eat the grass, it was actually an illusion of movement. The bugs on the side where there's a high density of grass repopulated, and the bugs on the other side where the grass had already been eaten died. So it's an illusion of I learned. So the population as a whole learned, but the individual trial really didn't extrapolate. It didn't have a neural network to extrapolate. What does this mean? All it knew was, I died, do something different.
Yeah, don't do that again,
Yeah.
right?
How do you iterate through
Yeah.
each organism in the population, and how do you decide when to generate the next set of population?
Okay. That is, let me pull up the code on that.
Could need to bring it on the screen.
So in the iteration, what we do is we,
So you need to hit the screen.
Oh. Thank you very much. There we go. That was really two different questions. The first one was, how do you decide when to apply the fitness function, or
when do you iterate through? So like you generate a population, and then you have to test each of them, but you only have one robot. So.
Right. Unlike bugs, which has like 1 million bugs, because there's only one robot, the population is really two. There's a current best, and then we mutate it into a test. So at any given iteration, we've got the current best gene, and we have the mutated test gene. Now, of course, we only have to run the test gene because we've already scored the best that we've done so far. And so it starts it off, the fitness function is go for 5 seconds, and then it scores it. And so now it has the two scores, the best, which it's already saved the score, and the test, which it just computed the score. And this is really simple. If GA test score is greater than the best score, then we kill off the best, make the test the new best, and then the next iteration, we mutate and make a new test from the now better best. So in this example, sort of a population of two. Selection is take the top one, kill off the other one, create one more mutant, and then go score it. Yes?
What do the numbers in GA best represent exactly? Like,
Okay, let's scroll up.
move this wheel by some speed, something like that?
Okay, in GA best of GA size, and GA size is the number of states times the number of values. So the data in the gene represents, for each of the states, 0, 0, 0, 1, 1, 0, 1, 1. A left value speed for the left wheel, a speed for the right wheel, and a delay of milliseconds on how long to maintain that speed in that direction.
Okay.
So the gene is 12 numbers, 3 for each of the 4 states, and then we just want to optimize that. So just a quick calculation, the search space of this, of course I would compare it to checkers. We've got basically 12 ints. Most of the ints are only 9-bit values, so we have 8 9-bit values, so that's 72. Actually, they're all 9-bit values, so we've got 12 times 9, so there's about 108 bits of state. Less than chess, more than tic-tac-toe. But just to give you an idea of the size of complexity of problems that this GA can solve. And I think it did a really good job. There wasn't really that many iterations for it to come up with a solution. So, but that's what the gene is for this guy. The smaller you make your gene, the faster it's going to learn, of course, because of that. That's what I didn't know when I was 10 and trying to solve checkers with 8 carbons.